Alright guys, so this week what we're going to cover is a little bit different than what we've done in the past. We're actually going to now start to deal with the econometrics or the statistics in this course. Luckily in Python and really any programming language, once you know how to do the programming, once you understand the basics of that language, you can pretty much implement regressions, t-tests, the stuff we're going to talk about today, with no more than a line or two of code. So today's discussion, we're going to go through these slides, which I will post online, but really what we're going to do is talk about how we set up a model, not in Python, but just in general. And then later, either this week or next week's lecture, I will post and go over another video where I talk about how to do this in Python. But again, if you have been keeping up with all the Python work to date, you're going to find that it is literally no more than a line or two of code depending on what you're trying to do. Okay, so what and why? What is this course? We've already talked about this a little bit. It is really just data science applied to finance. We're working with data, we're learning how to get insights from that data. So far, that's what you've actually been doing. You've been getting insights from it. What we're going to now do is continue to get insights, but we're going to use econometric models. We're going to learn how to test whether or not things are statistically meaningful. So why do we even study econometrics? Well, as I just mentioned, we're applying statistics to economic theories. We want to know more than just does it look like it matters? And now we're going to transition to does it matter statistically? Is there a statistical significance to our findings? So this is a way that we in finance, in economics, in just about any discipline, test out and confirm our theories. Do they make sense? Do they explain what we observe in the world? So what we're going to do is ultimately, by the end of today's lecture, understand how to present these theories or theories that you guys are going to come up with for your final projects in the form of a model, and then to test those models. See what the results are telling us. Okay, so why do we even have this whole field of econometrics? Well, normally, let's talk about healthcare, for example, we run experiments, right? We have individuals who get a drug and those who don't. You get a placebo, and we can test whether or not there's a significant difference in outcomes from that. But we can't really do that in economics or in finance, right? We can't say, well, what happens if we don't let this random sample go to college? How do their earnings change? Or what happens if we don't allow one company access to customers in a certain area and we randomize that? These can't happen. So econometrics has developed in order to provide us ways to examine these different impacts. Like, for example, what is the impact of size on firm performance or something along those lines? So we're going to use ordinary least squares, which is a type of regression, and we're going to use this method to test these different hypotheses, these different theories that we have about what's going on. And that's kind of what we're going to build up to. We're not going to do that first. We're going to start with a simple t-test, and I'll show you what that is when we get to it. And then we're going to look at single variable regressions and then multivariate regressions or multiple variables, all of which are very easy to do in Python, all of which are going to be easily accomplished with the skills you already have, and we'll get into that all. Okay, the implementation of econometrics, there's really 5 steps. Exploratory data analysis, this is what we've been doing so far. I've given you some data and you've explored it. You've told me things about it, you've transformed it into different variables, you've done a number of different things. This step, in all seriousness, takes about 80%, 90% of the time. Right? If your entire analysis takes 10 hours, you're probably spending 9 of those hours formatting the data, working with the data, understanding the data, transforming variables, getting it ready to run in the regression or in your model. Once you actually get to the model phase, it's very simple. Right? So we're going to specify the model that we want. We're going to estimate the model. We're going to determine what is the economic implications of that model. And sometimes you might try and forecast something in the future if that's what the purpose of your model is. In other words, are we trying to predict something from happening in the future, or are we just trying to explain something that's already happened? So those are the 5 steps to econometrics. One of the most common things you're going to do is variable transformation. And you've already been doing this, right? We need to create new variables that represent transformation of existing variables. And that's exactly what you're doing every time you've calculated returns, or every time you've calculated a portfolio of stock. Right? You are taking, in the case of returns, a variable, which is price. You're transforming it the first time to calculate a lagged price. So this is now a simple, very simple variable transformation. And then you're transforming it again. You're transforming two variables, price and lagged price, to create something called returns. So variable transformations are simple. You're just trying to convert one variable to something else to learn something new about that information. Okay, as I said, common example, returns from prices, and finances is probably the most common one you'll see. This is just kind of how we would remember that, right? We have a single period return, which is what we've done. It's the price today minus the price yesterday over the price yesterday. Or when we write it with subscripts, you can see here, price at time t minus price at time t minus 1 over price at time t minus 1, where t represents whatever period you're looking at. You might have prices today and tomorrow. You might have prices this month and last month. And you might have prices this year and last year. Whatever it is, t just represents that time period. And then we have our multi-period simple return, which is just the product of 1 plus the return minus 1. So again, these are just basic examples of what we talk about when we talk about variable transformations. Anytime you're turning one variable into something else, that's what we're referring to. Okay, so let's talk about our very first statistical concept or econometric concept, and that is your test statistic. Okay, we want to know, is something statistically significant? And what this means is, let's say, I would normally draw this out, but let's say we have two variables, or we have two samples. Both have an average value of 1. Okay, it doesn't really matter what these values represent, but one has an average value of 1 where all of the observations fall between 0.9 and 1.1. Okay, they're all very tightly clustered around that value of 1. In our second sample that also has a value average of 1, we have values that range all the way from negative 1,000 to positive 1,000. Right? They are all over the place. A huge dispersion of values. So on paper, if all we did is look at the average value, they look the exact same, right? We wouldn't be able to tell the difference between these two samples. But one of these two is much more likely to be a significant value. It's much more likely to have occurred because that is the real value, the real average, than by some random chance, right? That sample that has the values ranging from 0.9 to 1.1, very tightly clustered around the value of 1, that's likely to be a statistically significant value. It is significantly different than 0, right? It is not by random chance that has occurred that value different than 0, whereas if one that has an average of 1 where values range from negative 1,000 to positive 1,000, right, this huge spread, it's probably a pretty good chance that that is actually the result of chance. It is luck, right? Values are all over the place. There's a huge spread of values. It's unlikely that this value is statistically different from 0. Okay, and we're going to go through an example up here in a minute, but what this is trying to tell us is a value different from some other value? Most commonly done is whether or not it's statistically different from 0. So in other words, is a value different from 0? But you can really test this from anything. You could say, is the value, or if we have a set of returns, are these returns statistically different than 1? Then 5, then 0, whatever number you want, you'll see in the formula here. And once we do it in Python, how easy it is to change what we want to test it from. But this tells us there is a statistically different or statistically significant difference in these values. Okay? So here's the formula. T your t-value, your t-statistic, your t-stat, all three mean the same thing, is equal to the average, that's your x bar, minus mu sub 0 over standard error of your x values. Okay, where standard error of your x is going to be sy, which is your y values, over the square root of n, where sy is the square root of 1 over n minus 1, and so on and so on. Okay, so these are very long formulas. We're not doing them by hand. We don't need to do them by hand. We need to know how to interpret them. We need to know how to calculate them in Python. And we can go ahead and move forward with that formula. It is there for your reference, but you will never, in my class or in any class that I'm aware of in this finance curriculum, have to calculate these by hand. Okay, so confidence intervals. It's good to be aware of these as well. We can't know the exact value of an average when we are presented with a sample. In other words, if we want to know what is the average earnings of the United States, the way people calculate statistics and do this type of stuff is you're not actually going to get every single person in the United States salary, right? You're not going to know what their earnings are. You're not going to know the population mean. What happens is we calculate it from a sample. We take a sample of people in the United States and we calculate that as our average. Now, this does not give us the exact average. It gives us what is known as a confidence interval. We are going to say we are X% confident that our value falls between two numbers. Okay. So some examples, some commonly used ones. If we want to say the 90% confidence interval, okay, we are 90% confident that a value falls between the average of our sample, so if you calculated the average of the observations you have, plus 1.64 times the standard error of that average. So that'll give you the high end, right? If we had an average of 10, and let's just say, of 10, I can do this in my head. So that means that on the high end, we have 10 plus 16.4, or we're 90% confident that it falls below 26.4, or then we subtract, right? So that's the high end, and then the low end is 10 minus 16.4, or negative 6.4. So that is how we calculate standard errors, or how we use standard errors to calculate confidence intervals. If we want to be more confident, well, we have to, and finally at the most confident, we can say we're 99% confident that a value falls between. And that's all we really do. Okay, these standard errors are given to you when you run a regression. They're given to you as output, very basic, right there for you to read. So when we get into Python here later this week or this next week, we will see how that plays a role. Okay, so I've worked this through. I'm not going to post the answer here for just a second to give you guys a minute to calculate this yourself, but you guys saw the formula a couple slides ago. So let's use it. Suppose we have a sample of 200 recent college graduates. Okay, we have a hypothesis. This is what we want to test, that the average wage, the expected Y value, that's what the EY is $20 an hour. Okay, so that's our hypothesis. We want to say, do college graduates earn $20 an hour? We think they do. Obviously, 200 is not the full range of college graduates. It's our sample. So of those 200, the sample average wage is $22.64 an hour, and the sample standard deviation is $18.14. So with that being known, you can use the formula from the t-stat, and I'll show you here in a minute, to calculate that test statistic, and then we'll talk about using it. Okay, so first step, what is the sample error? What is the standard error of our sample? 1.28. What is the t-stat then? Right, it is the actual value minus our hypothesis, where that 20 is in there. If we were testing it different from 0, you'd replace the 20 with 0, whatever that number is, and then you're going to divide it by that standard error. So our t-stat is 2.06. What does that mean? Sorry. So how we determine this is a value is statistically different. It is statistically significant if the t-stat that we get is greater than 1.96. So this is a pretty basic rule of thumb. You can use this when we work on our final projects, when you work on anything you're doing. If you get a t-stat that is greater than 1.96, you can reject your null hypothesis, or in other words, you can say that the average of $20.64 is statistically different than your hypothesized value of 20. Right? These are statistically different, these values. Okay? So that is how we use it. You're going to get a t-stat. You're not going to have to calculate it. You're going to compare it to the value of 1.96. If it is greater than 1.96, it is significant. So, one thing to keep in mind, t-stats can be positive or negative, and it is perfectly fine if it's negative. We are not actually going to compare it, I guess, to this 1.96. You want to compare the absolute value. So a value of minus 2.06 is also significant, even though it is technically lower. So just keep that in mind. If you get a positive or negative number, you're just comparing it to 1.96. So if the magnitude of it is larger, then we can say it is a significant value. So let's put this into practice a little bit. The superintendent of an elementary school district must decide whether to hire additional teachers, and she wants our advice. If she hires the teachers, she's going to reduce the number of students per teacher, right? Obviously, when we have more teachers, class sizes go down. But there's an issue, right? Parents want smaller classes, but that costs money. This isn't free. So what do we do? Well, if she cuts class sizes, what will the effect on student performance be? In other words, this superintendent is asking us, does it make sense statistically to pay this extra money to hire more teachers? In other words, what is the effect on performance if we have more teachers, or in other words, have smaller class sizes? Okay, so we're going to take this test statistic that we just looked at, and we're going to use it to make this determination. We're going to use it from a linear regression, okay? We're going to look at the slope of the population regression line, right, where we're going to be looking at the expected effect on y of a unit change in x. In other words, if y is student performance and x is student to teacher ratio, or in simple terms, class size, we want to know, does a unit change in class size have an effect on y, or performance? So this is a simple regression. We're going to say, how does student-teacher ratio impact performance? Okay? So with that, the problem of statistical inference for linear regression is the same, right? We're going to look at how do we draw a straight line, and I'm going to show you this here in a minute, through the data to estimate the population slope. How do we test if the slope is 0, and how do we construct confidence intervals? So this is pretty much what we've just done. This is just going to allow us to build on and continue to add additional variables into our analysis. Okay, so this is what the regression looks like. We have test scores equals beta, that's what that b is, it's about beta 0, which is just our intercept from our regression, plus beta 1 times STR, student-teacher ratio. Okay, beta 1 is referred to as our coefficient. This is the impact that a 1 unit change in student-to-teacher ratio has on test scores, and we'll look at an example with numbers to make sense. Okay, so how do we calculate beta, or what is beta? Well, it is the change in test scores for a change in student-to-teacher ratio. That's all it is, it's just a ratio. or it's the slope of a line that best fits our data. Okay, so that was a specific one. This is how you write a generalized linear regression model. We don't say test scores equals student-teacher ratio. We say y equals beta 0 plus beta 1, x1, or xi, plus ui, where we can have as many variables as we want. X is known as our independent variable. Y is our dependent variable, right? So pretty much you can think of this as y is dependent on the value of x. Beta 0 is our intercept, beta 1 is our slope or our coefficient, and ui is just the regression error. In other words, we're not going to get every value correct. We're not going to be able to get an exact value from this. We are going to estimate the best fit line, the best value we can come up with, and u just is a measure of how close does our line actually fit the data. And that's what this is. So graphically, I think it's a little easier to see now. If all those dots represent the relationship between student-teacher ratio and test score, right? So let's just say, I don't know, this might be 17, where my mouse is. So if you have a observation that has a student-teacher ratio of 17 and a test score of 640, that's how we plot that point. Over here, student-teacher ratio, we find a class that has 20. We plot that point, and what is it, maybe 665 or so, I don't know. But that's really what we do. We plot all of our observations, and what this line represents is the regression line, our slope. It is the line that best fits our data. We're trying to minimize all of these error terms, where error terms are just the distance between the observed value and our estimated value, where the estimated values are this blue line, right? So if we run a regression to get a predicted value and we plugged in 20, right? So we said we have a student-teacher ratio of 20, our regression would estimate, let's just say that's 650. I'm guessing it's pretty close to that. So what would our error be? Well, the true value for this 20 is 665, where we measured it or estimated it at 650. That means our error, how much are we off by, is 15. So what a regression does is it calculates all of these individual errors and it fits this line. It keeps moving where this line is, keeps moving the slope of the line, keeps moving all aspects of that line to try and find the point where we have all the lowest error values. So we're trying to minimize that. So that's really all the regression is doing. We're trying to minimize this value, where beta 0 is our intercept, or where it crosses the axis at a value of 0, and beta 1 is the slope of this line. In other words, if we went from 20 to 21, a 1 unit change in x, right? We go from here to here. How much has our test score changed? Okay, so if we run this regression, you have test score equals, we get an intercept, and I'll show you this output here in a minute, 698.9 minus 2.28, where 2.28 is our coefficient times STR, student-teacher ratio. So this is what the output from this regression actually looks like. How do we interpret this? Well, districts with one more student per teacher ratio have test scores that are 2.28 points lower, right? You have more students, or larger classes have lower test scores. For every additional student that you have in your class per teacher, test scores go down by 2.28, right? But obviously we need a starting point. Test scores don't start at 0. That's really what this intercept takes care of, right? So the test scores in this district, let's say, start at 698.9. If there's a 0 here for student-teacher ratio, obviously that can't realistically happen, a 0. But really that's all we're doing to calculate this or interpret it. 698.9 minus excuse me, 2.28 times student-teacher ratio. And that's really what this text here says. You can check this out in the notes if you need a reminder. But here we go. So one of the districts in the data set's Antelope, California, for which student-teacher ratio is 19.33 and test scores are 657.8. So how do we get a predicted value? What do we think the test score is going to actually be? We know the real one. What does our regression tell us it's going to be, right? This is the regression equation from the prior line. This, what we call is a hat. It's kind of just this little caret above test score. That means predicted. So what does our regression predict test scores will be? Well, 698.9 minus 2.28 times the student-teacher ratio, 19.33, we predicted a value of 654.8. We know the actual is 657.8, so we can calculate the residual, that error term. How good did our regression do? Well, it was off by 3, right? We estimated 3 points lower than they actually got. Okay, so we know that we messed up by 3. Is that a good value? Is it a bad value? We don't really know. So that brings us to measures of fit. 2 regression statistics are going to provide us some information. We're going to really focus on one. But what we want to know is how well does our data and our estimate fit, right? So does our line, I'm going to go back to, does this line here, this blue line, fit the data well or not? Is our regression doing a good job of explaining our results? Okay, so we have regression r squared, which just measures the fraction of the variance of y that is explained by x. It ranges from 0 to 1. In other words, how much of the test scores, the variance that we observe in test scores, is explained by the student-to-teacher ratio. A value of 1 means that all the dots that we saw in that prior slide landed exactly on that line. That would be a value of 1. We explain it perfectly. We have 0 error terms. And a value of 0 means that there is no explanatory power. Student-teacher ratio has no ability to tell us what performance is going to be at for that school. Okay, and adjusted r squared just has a built-in penalty for adding more variables. When we get to multivariate regression, you'll see this. With a single variable, it doesn't matter. But pretty much what it's saying is if you add additional variables to the regression, your r squared should go up on its own regardless of how well the regression is actually performing. Adjusted r squared just accounts for that. And the other one, we're not going to talk about it much. You should know it exists. Standard error of the regression is just the magnitude of typical regression residual in the units of y. Again, be aware of it, but we're going to focus on r squareds. Okay, so I'm going to talk through the formula really quickly, but we're not going to care about the formula beyond knowing that we have access to it here, because we are going to have Python or whatever program you choose to use in the future give us this value. Okay, so let's just jump down to here. Total sum of squares equals the explained sum of squares plus residual sum of squares. Okay, where we have the explained sum of squares over total sum of squares is equal to the sum of your predicted y value minus your average predicted y value squared over your sum of your actual y value minus your y average squared. And this gets really complicated really quick. Again, you can do these calculations if you wish, but this value is provided to you right here in a minute where we look at this. Okay, so the question we have to tie all that we've just done together, and we're going to look at it. An angry taxpayer claims class size has no effect on test scores. We're saying, essentially, is this true? We can test it through 3 simple steps. Oh, that's a typo. It should say compute, not computer. Compute the standard error of our y's. It's an estimator of the standard deviation of the sample of y. We're going to then, once we have that, right, because we have the standard error of y down here, we're going to calculate the test statistic. In other words, our average value minus whatever value we're testing. In this case, it's going to be 0. We want to know, is there an actual impact from the class size over standard error of y? And we're going to compare the t-stat to a value of 1.96. So this is output from SAS. When I go through, this is just another statistical program. It's pretty much going to be the exact same output you're going to get for Python. It's just going to be formatted a little differently. All the variables are the same. Okay, so what we're going to have in this data that I will provide you probably later this week on D2L, along with me going through running it, 420 observations in that data. We're going to run a regression. And what we're going to have, intercept, or our B0. You notice this matches exactly to what we saw in the notes. Okay, you're going to run a regression with a single line of code. Intercept, well, 698.93. STR, student-to-teacher ratio. Larger classes, test scores go down by 2.28 rounded points. And we notice that our t-value is significantly different. Right? It is a large number. 4.75 is larger than 1.96. Remember, it doesn't matter if it's positive or negative. We're looking at the magnitude, the absolute value of it. So this is a significant value. What does that mean for us? Oops, sorry. What this means is that we can say student-to-teacher ratio has a significant impact on test scores. If we drop student-to-teacher ratio, in other words, if it goes down by 1, right? So that change is a -1. That means test scores go up, right? Negative 2.28 times -1 is a positive 2.28. For every class or student-teacher ratio increase, test scores go up. Or I'm sorry, for every increase in class size of 1 unit, test scores go up. If we reduce class size, test scores are improving. Okay guys, so what we're going to look at here is just a very short bit of code. As I said, it's not very challenging to run this and to get a regression from your data. So I'm going to clear my output and I'll be posting this to D2L along with the data set. Okay. Alright, so let's start with this. We're going to have our normal import pandas is PD, import numpy is NP. We're not going to import a new library. Now we could do import stat models as whatever we wanted to, so we didn't have to write out the word stat models, SM if you wanted, but we're not needing everything that's within stat models, right? There's going to be a ton of different functions in there, and we are explicitly using one and only one, and that is OLS. So we're going to write a little bit of a different method for importing this library. We're going to say from statsmodels.formula.api import OLS. And if you actually Google stats models and you go to their webpage, it'll show you all these different steps and how you can do this, but I'm showing you exactly how to do it. This is the regression we had talked about, ordinary least squares. So that's all we're going to do. We're going to import this one small function from within this library. Here's the main library, and then we're drilling down different levels until we get to OLS. Now I'm providing you with this CSV file. It's going to be right here in your desktop, or I have it, week 4, and there it is, CA for California School. I'll be uploading this. So we're just going to read it and open it, and I'm just going to type info to get a sense of what it looks like. And I actually forgot to run our first line of code. That's why it says PD is not defined, because you can see I haven't run this up here. So let's come back up, run that, and the school. Okay, so what we're going to try and do is replicate what we saw in these slides, and you're going to see how to do that. Okay, so we have this data set has 420 observations, numbered 0 to 419. And these are all the variables that we have, and we'll start dealing with a bunch of these next class. For now, all we're doing is looking at, let me find it, test score, so TS, TSCR, and STR. We want to know what is the impact of changing your student-to-teacher ratio on your test scores. So I just want to dive into the data a little bit, make sure everything looks like it should. So I'm going to hit a describe. We can see all of them have their variables. Test scores, we have a mean of 19.64. I'm sorry, for student-teacher ratio, test score is 654. We can kind of just eyeball what's going on. Okay, so if I come down here, here we go. This is our new code. I told you it was very easy. Once you have your data set up in the format you want, in other words, let's say we wanted to know what was the impact of stock size on returns. While you calculate your returns, we could get stock size from another data set, merge them together, and then you have everything you need. For this test, we have everything we already need provided to us because we're not here to practice the cleaning and preparation of the file. We want to understand how to run and interpret a regression. Okay, so reg out, this is what I've called it. You can call it whatever you want. I'll just call it output. So you can see that it doesn't matter what you call it. We're going to say equals OLS. Okay, we're calling the ordinary least squares function, and we open and we close parentheses. Okay, this is what it's going to look like. Within that parenthesis, in a quote, single or double, we're going to type test score. This is a tilde. It is the key to the left of the number 1. So hit shift and that key to the left of number 1. Okay? str. So this is our regression. This is our y equals x. And we don't have to put anything for that beta 0 or that intercept. It knows it is going to be there. And we put a comma, and then we tell it what data set. Remember, I called it school. And finally, what we have is, there's a couple ways of doing this, but we're going to do it where we write .fit. So what it's going to do is it's going to fit that line that we discussed in the slides. It's going to come up with that line, and it's going to save all of that output to this file called output. So we're going to run this, and nothing's going to happen. You're going to see it run, but no output. And why is that? Because all of our output that we would care about is saved in this output file. So let's look at summary. Here's our summary. Here's our dependent variable, test score. The model is OLS. Method is least squares, right? Some date, time, things we don't really care about. I'm recording it this morning. Number of observations, 420. Other things we've mentioned, here's your R squared and your adjusted R squared, okay? Coming down, this is where it's most important. If you remember the notes, if you remember the answers we got in those notes, the intercept, that beta 0, 698.93, str negative 2.2798. So these are the coefficients. What we look at next is the t-stat, right? This is a t-stat which is greater in magnitude than 1.96, so we know that there is a significant impact on test scores from a change in the student-teacher ratio, right? The more students we have in a class, the lower the test score. And the reason why we do this .fit, we can do summary and get this, but if we don't want all these details, we can get a lot of other things. So output.params, there's our intercept and our str. We don't know what the t-stats are, but maybe we don't care right now. We can get things like the R squared only. So we're able, see, 0.051, we're able to pull out individual aspects of it when we save it to a file. So all this is there for us to come back to later on. So that's it. That's how you run a single variable regression. I do want to talk about one new Python bit of code, how we use that to run a regression in a little bit of a different way, and how we interpret that. Okay, so maybe we don't care about the number of students per teacher. Maybe what we care about is just some cutoff. What's the impact of having a student-to-teacher ratio less than 20 or greater than 20? Maybe that's the number that we want to know. If we get everybody below 20 or the average number of schools below 20, is that going to benefit the students? So with the original number, we don't know specifically what that impact from 20 is. What we can do here is create a dummy variable or an indicator variable. It just takes on a value of 1 or 0. And what we do is we take our original file, school, I'll do it up here. Let's do small variable. We'll call it something new. So we're adding a new variable called small variable. How are we doing that? Well, we do np.where for his numpy. We haven't actually referenced numpy yet, right? We've always done things with pandas, but np is the other library we've been loading. So we say where, because we're going to say, it's almost like your if statement, okay? If something happens, do this. If it doesn't happen, do that. Or if something is true, return value A. If something is not true, return value B. So we're going to say school str. So we say np.where school str. In other words, we're going to do something that references the student to teacher ratio. And let's say if it's less than 20. So if there's less than 20 students per teacher, comma, what do we want to return? A 1. If it's not a 1, it's a 0. Okay, so that's all we're doing. And what this is saying, make a new variable, small variable, where school file student teacher ratio column is less than 20, fill a 1 into small variable. If it's not a 1, fill a 0. Okay, and there we go. Small variable, 1, yep, under 20, over 20, 0, under 20, under 20, under 20, all 1s. Okay, so that's it. That's how you make this variable. And if we want to learn whether or not, if we want to determine whether or not this variable, this class size of 20 is meaningful, we can just run another regression. And we'll look at that and we'll look at how to interpret it. So let me pull that up. Okay, so here we go. It's no longer called small class, I called it small variable. So we're going to run the same setup. We're going to save our regression results to reg_dummy. Regression dummy is going to be equal to OLS, our test score. And this time we want to know, does a small class, in other words under 20, have any impact? So we'll fit it and we will run it. So here we go. First off, the small variable is positive, large, and significant. It is greater than 1.96. So where the last one we interpreted as for every additional student in that student-teacher ratio, it was a 1 unit change. So if you had 2 students, it would have been that 2.28 or something? That 2.28 times 2, 3 students times 3, 4 students times 4, and so on. When you have an indicator variable or a dummy variable, you can't keep adding to that, right? It's not like the student-teacher ratio where it's a continuous variable that keeps on changing. This case, it's either a 1 or a 0. So if you have a large class, you put a 0 here. It would be the intercept plus 7.3724 times 0, or in other words, just the intercept. That's the average test score for large classes. If we have a small class, it is 649 plus our beta 1, 7.3724 times 1, right? So that is how we introduce and deal with dummy variables. Those are the 2 types of simple single variable regressions we're going to talk about. The one where we have a continuous variable where it's for a 1 unit change in student-teacher ratio, and that can be 1 unit. We could have units change by 2, by 3, by 4, by 5, whatever the number may be. They can be positive and negative. You could have student-teacher ratios going down, as opposed to this dummy variable where we now want to know, what about classes that are bigger than or smaller than 20? In this case, you make your new variable. You create a variable transformation, run your regression, and that is the impact. It's either we add 7.37 points if we have a small class, or we add 0 points if we have a large class. So that's it for single variable. Next week, what I'm going to do is upload the slides for a multivariate regression. I will tell you right now, it is just as easy as this. We're just going to add additional variables, and we're going to talk about how you interpret that regression. It'll probably be a 10-minute lecture at most. I will introduce your final project, including the data set. That is not going to be terribly difficult either, and we will be good to go.